Welcome everybody. This is quantum tutorial, second day, Tuesday, and today we're going to talk about how to solve quantum chemistry problems using variational quantum algorithms. Today's speaker is Dmitry Fedorov from Macron National Lab. He had lots of experience with VQE. Dmitry, it's all yours.
Thank you, Yuri, for the introduction. My name is Dmitry Fedorov. I'm a postdoc here at Argonne National Lab. I work with Yuri Alexeyev on simulating quantum chemistry using quantum computers, and one of the main fields is the variational quantum eigensolver that I'm going to talk about today. First, a brief outline of my talk. First, I'll mention a few quantum algorithms, how they are designed, and what's the should be the benefit of them. Then I'll talk about I'll introduce the electronic structure problem, the main problem of quantum chemistry, and how we can simulate these problems on quantum computers. And then I'll switch to the details of how variational quantum eigensolver works and its main parts, such as mapping of the Hamiltonian onto qubits, quantum classical loop for finding eigenvalues, and one of the most important parts is the parametrization of the wave function, pros and cons of different approaches, and I will end with the achievements of this method and the main challenges. So what are quantum algorithms? They are not just, so first of all, quantum computers are not just faster computers that can magically solve the classical problems faster. Quantum computers use the quantum effects such as superposition and entanglement to get a speed up or some other efficiency improvement over any possible classical algorithm. And some of the examples, obviously not all of them, but one of the more famous algorithms are Schur's algorithm, which used for prime number factorization, which are used in the RSA encryption. HHL algorithm that's used for solving linear systems of linear equations, which is obviously a very common problem in various fields. Grover's algorithm that's used for database search, and quantum phase estimation, which I'll briefly mention during my talk, which is used for finding eigenvalues of unitary operators. However, during this time where we don't have large-scale quantum computers that are required for fully quantum algorithms, we work with hybrid quantum classical algorithms. So today I'm going to talk about the variational quantum eigensolver, which is used to find eigenvalues of the Hamiltonian. And tomorrow, in this workshop, you will learn about the QA-OA algorithm that's used for optimization problems. So let's start with the quantum chemistry and electronic structure problem and how it has been done on the classical computers for the last many decades. So you start with the molecular time-independent Schrödinger equation, where H is the Hamiltonian of the system, psi is the molecular wave function that depends on the coordinates of the electrons and the nuclei, and E are the eigenvalues of this Hamiltonian, or the energy of the system. So in atomic units that are commonly used in quantum chemistry, this molecular Hamiltonian takes this form. In atomic units, the Planck constant is equal to 1, and also the charge of electron also equals to 1. That's why it might be different from what you've seen before. So this first term is the nuclear kinetic energy, where capital indices label nuclei, the lowercase indices label the electrons. The second term is the kinetic energy of electrons. Then you have the potential energy of interaction of the nuclei with electrons, nuclear repulsion, and finally the potential energy of the interaction of electrons. And so this is this equation, this Hamiltonian can be solved exactly, and one of the most common approximations that's done in quantum chemistry is Born-Oppenheimer approximation, which separates the electronic and nuclear motions, which is written over here, which is essentially neglects the nuclear kinetic energy, because the nuclei are much heavier than electrons, and the electrons adjust instantaneously to the movement of the nuclei. Therefore, we can set this kinetic energy of nuclei to 0, and this term that's easy to compute, the nuclear repulsion, you can just add it to the total energy afterwards. So we are solving this eigenvalue problem for the electronic Hamiltonian, which contains these 3 terms. And this is one of the main problems in quantum chemistry that's been solved. And once, if you compute these energies for multiple internuclear distances, you can use this potential energy surface to describe the nuclear motion. So even though this is an easier equation to solve, it still can be solved exactly. It only can be solved for hydrogen-like atoms with 1 electron exactly. So quantum chemistry deals with the approximate solution of this problem on classical computers. And so when we talk about approximate solution, so how close do we need to be to capture to the real true energies to capture the important chemistry? So there's a term of chemical accuracy. When you have some reaction, so here you have potential energy of some system. So here is energy, and here is reaction coordinate. And you start with the reactants, and you end up with products here. And to get to the finish, you need to overcome this activation energy or reaction barrier. And the rate of the reaction, according to this Arrhenius equation, is depends exponentially on this activation energy. And error in thermochemical experiments is on an order of 1 kilocalorie per mole, which translates into error in reaction rate of around 10. Basically, if your energies are within 1 kilocalorie per mole, your reaction rate is correct with up to a factor of 1 order of magnitude. And if we talk about the atomic units, this 1 kilocalorie per mole is 1.6 millihartree, where hartree is the unit of energy in atomic units. And so this is the number we basically put for when we run the calculations of energies, if we want to be within chemical accuracy. So one of the most, not the only one, but one of the common methods to approach this problem is to represent the electronic wave function using atomic-centered Gaussian basis functions. And Molecular orbitals are simply linear combinations of these atomic orbitals. And for simplest system H2 with minimal basis set, where you have one basis function for one atomic orbital, you have these two atomic orbitals with one electron on each orbital. And these atomic orbitals form two molecular orbitals, the bonding and anti-bonding one. And the total electronic wave function is represented as a so-called Slater determinant, which is anti-symmetric to satisfy the Pauli exclusion principle, which states that if you exchange two electrons, your wave function needs to change its sign. So once we introduce the electronic wave function representation, we need to solve the electronic time independent Schrödinger equation. So this is the molecular orbital diagram where you have some occupied orbitals and virtual orbitals, and this configuration, electron configuration, corresponds to the mean field solution of this equation, where you essentially each electron moves in a field created by all other electrons, and so you don't capture the effects of interaction of each pair of electrons. This is a very crude approximation, but it serves as a starting point for more complex methods that take into account other possible configurations. So here you have the singly excited electron configuration, where you excite one electron from this Hartree-Fock mean field approximation. This one takes into account double excitations, and you can go further and further. Some of the methods, which are called post-Hartree-Fock methods, include coupled cluster, configuration interaction, multi-configurational, self-Hartree-Fock, and full configuration interaction. So the energy between the true value and the Hartree-Fock energy is called the correlation energy, and that's essentially what we want to find. It is a small amount of energy compared to the Hartree-Fock energy, but this is actually where all important chemistry happens. And the full CI method that considers all possible configurations up to all possible configurations provides an exact solution for a given basis set, and is considered is usually used as a benchmark. It is not very useful for running simulations on large molecules, because it's the number of electron configurations or these determinants grows exponentially, so it gets intractable very fast. And that's where the quantum computing comes in, with a promise of avoiding this exponential limitation of this exponential growth. So it's started with several decades ago, and Richard Feynman noted that the nature is not classical, and if you want to simulate the nature, you need to treat it quantum mechanically. In other words, you need a quantum computer to simulate quantum systems efficiently and accurately. And so, as you've probably learned yesterday, the difference between classical bits and quantum bits. So for an array of n bits, you have 2 to the power of n possible states, and your system is in one of those states. And for an array of n qubits, you have the same number of possible states, but your system can be in a superposition of that state, of those states. And just to store the state of the system for 50 qubits on a classical computer requires 16 petabytes of storage, and it increases by a factor of 2 once you add extra single qubit. And so the idea for simulating quantum systems on quantum computers is that you start with your quantum system or your molecule that you want to investigate. You map it onto the quantum computer, which is controllable and tunable, where you can prepare the state that corresponds to the initial state of your system, evolve it in a controllable manner, and measure its state or its energy in the end, and then therefore you learn the properties of your quantum systems. It's important to note the differences between the digital versus universal quantum computing. In analog,
Dmitry, we have a question here.
Yeah.
So it's from Ish. What applications quantum chemistry need correlation energy, and why Hartree-Fock is not enough?
Yeah, well, essentially, just getting the energy gaps for some excitation energies from one state to another. Basically, Hartree-Fock is not good for basically anything other than using it as a reference wave function. In some cases, it works okay, but it's not reliable, and you don't know in advance. So you always want to use some higher level method.
And what other applications?
Applications of Hartree-Fock?
No, post Hartree-Fock, I guess, methods.
What do you mean applications? Sorry, I'm not sure I understand.
Here exactly is the question. In what applications in chemistry would correlation energy matter?
Well, it all comes down to the so that there is the for example, when you break bonds and you have molecular orbitals that become degenerate, and Hartree-Fock, for example, puts if you talk about hydrogen atom that I described before, it dissociates hydrogen molecule into hydrogen ion with 2 electrons and a proton, which is completely wrong because it will dissociate into atoms, and that's what's called the static correlation energy, where you have degenerate molecular orbitals. And there's another kind which is called the dynamic, where you essentially need more basis functions to account for more electron configurations, excited electron configurations. But yeah, the best example is probably the dissociation of even H2, which is completely wrong if you do it with Hartree-Fock, not even qualitatively.
Yeah, maybe I can add that usually computing chemical properties at very high accuracy requires, for example, in the textbooks for chemistry, when you see thermodynamics data, like enthalpy of reactions, usually like we are done at very high accuracy. We are usually very highly accurate calculations, and this is where you need correlation shortcuts. All right, Dmitry, please continue.
All right. So in analog quantum computation, you map the quantum system of interest onto the simulator, and that simulator is controllable and has tunable parameters. And by varying these parameters, you study the system in different regimes. But we're going to focus on the digital quantum computing, where the evolution of the Hamiltonian is decomposed into a set of elementary quantum gates, and you use some algorithm to find the eigenvalues of this Hamiltonian. And essentially, you can do this to any Hamiltonian. You can decompose it into a set of elementary gates, whereas for the digital quantum computation, you have a lot of restrictions in terms of what Hamiltonians you can map onto your particular analog quantum device. And so one of the algorithms that can find the eigenvalues of the unitary operators on quantum computers is the quantum phase estimation, which was introduced around 20 years ago. It's proven to provide exponential speed up for finding eigenvalues of the unitary operators. Essentially, if you can prepare some approximate eigenstate of the unitary operator e to the power I phi, you can compute the eigenvalues of this operator using this ancilla register that you use the Hadamard gates to put into superposition of states, so that any state can be prepared. And on this, the wave function is encoded into this main register, and by applying these controlled rotational gates, you change the phase, and essentially you measure this phase in the end by applying this quantum Fourier transform. You convert from the bit strings of 0 and 1s into phase, and that phase is basically encoding of the eigenvalues of the Hamiltonian. Obviously, it's a very quick explanation, and it's not enough to understand this method, but essentially, it has been mathematically proven that this is the algorithm that provides exponential speedup over any classical algorithm for finding eigenvalues and eigenvectors. And by increasing the number of these ancilla qubits, you can systematically improve the precision. And you have to repeat this process to achieve precision epsilon. You have to do the 1 over number of measurements proportional to 1 over epsilon. So this is all great, and it's proven mathematically it will work. But the main problem is that for any useful system that can be studied with classical computers, this algorithm would require thousands of qubits and millions and billions of gates, which is many years away from being a reality. This is the roadmap for the IBM quantum computers, and they are expecting to have a quantum computer with around 1,000 qubits in 2023. And obviously now it's limited to under 100 qubits, which also have in some cases, very large error rates. And fully quantum algorithms are not useful yet on modern quantum hardware. And so the question is, in this noisy intermediate scale quantum or NISQ era, what can we do on modern quantum hardware. And one of the things that we can do is the hybrid quantum classical algorithms and in particular, variational quantum eigensolver that I'm gonna talk about. So the main pieces of this method are the mapping of your Hamiltonian onto qubits, parametrization of the wave function. So you basically need to pick the unitary operator that's going to prepare your wave function from the initial guess of the mean field Hartree-Fock solution, which is easily done on a classical computer. And then you use the classical optimization to minimize the energy with respect to these variational parameters. And according to variational principle, if you do it this way, you always your energy guess for your guess for the energy always stays above the real ground state value. So this is the hybrid method where energy of the Hamiltonian is computed on a quantum computer, and the variational parameters are optimized on a classical computer, and that way some of the computational burden is offloaded to a classical computer because quantum hardware is not capable of running long circuits nowadays. So before we go further, the Hamiltonian I showed you before is written in so-called first quantization formalism, and it has these two terms that involve one electron, and this term involves two electrons. And for mapping to quantum computers, the more convenient representation is so-called second quantization, which is basically occupation number representation. It has these two terms, one electron term and two electron term. These AP dagger and AQ are creation and annihilation operator. A dagger basically creates electron on orbital p, and AQ annihilates or destroys the electron on orbital q. Similarly, for the two electron processes, you create two electrons on orbitals p and q, and you remove electrons from orbitals r and s. And these HPQ and HPQRS are called 1 and 2 electron integrals that are written over here. These are easily computed on a classical computer before you start the simulations on using VQE. So how do we map the system of fermions to qubits? So as you probably know, the electrons are fermionic particles. They are indistinguishable, and they need to obey the Pauli exclusion principle, whereas qubits are distinguishable, so they have different commutation relations. There are multiple ways to map fermions to qubits, but probably the most chemically intuitive is the Jordan-Wigner transformation, where each spin orbital, so alpha or beta, spin 1/2 or spin minus 1/2, is mapped onto a qubit, where 0 state of a qubit corresponds to an unoccupied orbital and 1 corresponds to occupied orbital. And the occupation here in this mappings is stored locally on each qubit, and the parity is non-local. And this scaling in terms of gates of this mapping, asymptotic scaling is O of n. Other mappings, such as parity, It's sort of inverse of Jordan-Wigner, where parity is stored locally, but occupation is non-local with the same asymptotic scaling. More complex mapping is Bravai-Kitaev. It's middle ground. It has more complex structure, and the scaling is logarithmically better when you use that mapping. So when you map...
Dmitry, we have a question here.
Yeah.
We need to stop periodically and ask if people have any questions.
All right, I will continue.
Yes, please go ahead.
So when we map fermions to qubits, as I described in the previous slide, we obtain up to n to the power of 4 terms in the Hamiltonian, where each term is a product of polystring with some coefficient alpha, where this coefficient depends on the 1 and 2 electron integrals HPQ and HPQRS. And this polystring is essentially a product of the poly matrices, which are written right here. And in any of the mappings, you always end up with this form of the Hamiltonian with multiple terms, polystrings with the coefficient in front of them. So to give you an example, as I said, when we look at electrons and you work with spin orbitals, so when you have, as in case for H2, you have 2 spatial orbitals and 4 spin orbitals, so you can label them 0, 1, 2, 3. You can directly map it onto the qubits, 0, 1, 2, 3. So fermionic Hamiltonian for hydrogen molecule with minimal basis set using Jordan-Wigner transform has these terms where each of them has these creation and annihilation operators and some coefficient that depends on the molecule and atomic positions. And when you map it onto qubits, you have these terms that contain polystrings and the coefficients in front of them. And as I said, these coefficients alpha here depend on the molecule and positions, atomic positions, but these operators are going to be the same for any particular system with a certain number of electrons and orbitals. All right. So this is the flowchart of the VQE method. As I said before, you start with the fermionic Hamiltonian problem on a classical computer. You do the mean field Hartree-Fock solution. So all these green boxes are operations performed on a classical computer. When you map problem onto qubits, you get these sum of the polystrings, and you need to generate the Danzatz to represent the wave function. So this operator U, parametrized operator, is essentially your Danzatz that prepares the trial state from the Hartree-Fock initial guess. And then you prepare this quantum state on a quantum computer using parametrized quantum gates. And then you measure the energy of the system on the quantum computer. And using classical optimization, you update these parameters to minimize the energy, and in iterative fashion, you minimize the energy and hopefully converge to the ground state of your system. So to say a few words about the measurement process of the Hamiltonian. So your energy is essentially a sum of these matrix elements where, so these are the coefficients that come from the Hamiltonian. These here are the poly strings, and these are variational forms. So when you measure the quantum circuit, you get essentially some probabilistic outcome, and you have to repeat the measurements to get together the statistics. So you have to measure, you have to prepare each of the the circuits for each Hamiltonian term separately and measure it. And on top of it, you also have to, as I said, repeat this multiple times to get statistics. And the number of the measurements to achieve precision epsilon scales asymptotically as 1 over epsilon squared, compared to the QPE, which only needs 1 over epsilon measurements. Are there any questions up to this point?
This is more like comment from Ish. A long one. It's about correlation energy.
Should I read it, or should we leave it for later?
Yeah, let's talk about this later.
Okay. So now let's talk about the wave function parametrization. So basically, this parameterized unitary operator is a quantum circuit, can be represented by a 2 to the power of n by 2 to the power of n matrix, where n is the number of qubits, and it's basically a product of the quantum gates, and can be single or multi-qubit gates, parametrized or non-parametrized. So as you can imagine, there is many ways how you can represent this operator. And the requirements for a good ansatz for NISQ devices, because there are high error rates and limited quantum coherence, we need short circuits. So the number of gates needs to be as small as possible. Also, we don't want too many parametrized gates, because then it becomes a hard problem for classical optimization when you have to deal with large number of parameters. And also the ansatz need to span the space which includes the solution, because if there is no way to get if it can generate the state that's your solution, you will never find you will never converge to that solution. And so one of the first introduced ways of parameterize this wave function is the unitary coupled cluster method, which is a unitary version of the classical coupled cluster method. So, which essentially has these excitation operators that similarly to how we generate the qubit, the Hamiltonian, electronic Hamiltonian, we have some reference state, which is the Hartree-Fock, and then you excite the electrons using T1 operator. You obtain the singly excited configurations, and using T2 operator, you get the doubly excited. And so these parameters here, tau, are the cluster amplitudes, and these are parameters that we are going to parameterize. So for each excitation, single or double, you're going to have a variational parameter that adjust these amplitudes to minimize the energy. And so in a regular coupled cluster, the wave function looks like just the exponentiated cluster operator T. And this method can be implemented on a quantum computer because this is not a unitary operator. And for a digital quantum computation, all operators have to be unitary. So we use the unitary version of this, which is essentially instead of exponentiating T, we exponentiate T minus complex conjugate of T. And for this method, there is no efficient implementation on classical computers, but it is easy to implement on the quantum hardware. And if we look more closely onto what kind of circuits we obtain with this variational form, essentially, as I said, for one excitation, you get one variational parameter, which is so for T1 is this rotational gate theta. For T2, there's also one parameter here. And to enforce the parity of the anti-symmetry of the wave function, we end up with these cascades of C-NOT gates, which are controlled NOT gates, 2-qubit gates that basically have to connect all the qubits between the qubits from which we perform the excitation up to the qubit to which we perform the excitation. And essentially, this enforcement of symmetry, anti-symmetry comes at a high cost because these 2-qubit gates on modern devices contribute a lot of noise to the simulation. So here's the map of the IBM Manhattan device with 65 qubits, and the for example, for a single qubit gate, the error is on order of 10 to the minus 4. However, when we talk about the C-NOT gates, which are 2-qubit gates, the error is 2 orders of magnitude higher, and therefore, when you have too many of these, you get too much noise that you're not getting anything meaningful as a result. And so the question is there a way to reduce the number of 2-qubit gates in Danzatz? So the solution was proposed by the scientists at IBM, where they did suggested to use so-called hardware efficient Danzatz, which is basically a certain number of repeated blocks of entangling gates that entangle the qubits, so they have multi-qubit gates such as C-NOTs, and parametrized single qubit gates, and they pick the gates that they include here. They pick from the gates that are naturally available for a certain quantum computer. So the properties of these ansatz is essentially a relatively small number of 2-qubit gates. However, you end up with a lot more variational parameters because you have you parameterize all these single qubit gates, and you have to optimize a lot more parameters compared to the UCCSD ansatz. And also there is no symmetries built into this ansatz because it's there's no chemistry involved in designing these, essentially. And the idea is that by increasing the number of these layers, this D parameter, when you add these blocks one after another, you increase the expressibility, which means that you can obtain the solution space that you can that you're getting increases. So couple words about expressibility that's related to the problems that this Danzatz causes. Essentially, when you have this space, this is the space that this blue ellipsis is accessible space by a certain unitary operator. And so it contains the solution to problem A, but doesn't contain the solution to problem B. And we want to look at the cost function, so basically energy. We look at the landscape, what it looks like around the minimum point. So in this case, we can have a landscape that looks like these, or this, where you have a much smaller region with non-zero derivatives, right? And once you increase the expressibility, in this case here, which includes solution to both of these problems, you are bound to have this kind of cost function landscape, where essentially you have this small region where you have the derivative of energy that's not zero, but in all other regions, the derivative essentially is zero. And this causes problems like when you start in one of these points here, when the gradient is zero, you can't update the parameters to minimize the energy. And this problem is called barren plateaus, which was there was a paper a couple of years ago where it has been shown that with increasing number of qubits for a random hardware efficient ansatz, the variance of the gradients that's here of energy gradients decreases, variance decreases exponentially. And what you're getting, that essentially there is no way you can optimize, find the minimum of the energy unless you start in this tiny region that gets exponentially small with increasing number of qubits. And so this is probably the biggest disadvantage of the hardware efficient ansatz. You can mitigate this by, first of all, if you somehow can come up with initial parameters, a good guess for initial parameters, or you can add layers one by one or optimize one at a time and initialize blocks so that they act as identities. So basically zero them out and then optimize them block by block. So using hardware efficient ansatz, at IBM, they have done these experiments on the real quantum hardware for, so these are H2 molecule and the lithium H molecule, where they plotted these potential energy surfaces, and they did some error mitigation, which I'm not going to get into right now, but essentially what they could achieve here on this insert on the bottom, you see the errors in terms of millihartree. So remember, the chemical accuracy is 1.6 millihartree, and here you see the points that are higher by tens of millihartree, which is far from accuracy, chemical accuracy. For sodium H, which they also reduced to for qubits, they also get errors on the order of tens of millihartree. And this emphasizes how difficult it is to run any simulations on hardware, even for small systems. But the hardware is improving, and it's important to work on the algorithms for later use. And so here I put a table with main achievements of running simulations on quantum hardware. So this is the number of qubits for the problem. So the largest here is 12, where Google ran Hartree-Fock simulation on a quantum computer, which is not as hard as running unitary coupled cluster, for example. For unitary coupled cluster, I think the maximum number of qubits is 4, and for hardware efficient Danzatz, it's 6 qubit problems that they've done on actual quantum hardware. So to summarize the pros and cons of different ansatzes, for chemistry-inspired unitary coupled cluster, you get advantage such as you have to deal with a small number of parameters usually compared to hardware efficient ansatz. The results are easier to interpret because it's constructed from chemistry. And it also gives you a benefit that some symmetries such as parity are automatically enforced. The obvious disadvantages for NISQ hardware is the very long circuits with many 2-qubit gates, multi-qubit gates in general. And as for hardware efficient ansatz, it's more expressible, easier to run on hardware, but it can be very inefficient when you spend too much Hilbert space and you have to optimize a large number of parameters, and you might encounter barren plateaus, and you also don't have to enforce symmetries. Additionally, there are ways how to do it, but it is extra work that needs to be done to enforce those symmetries if you want to have the solution that's restricted to the physical results. And to sum up, variational quantum eigensolver is a near-term alternative to the quantum phase estimation algorithm. And still, the modern hardware is not good enough to run the simulations that are not possible on classical computers yet. And more efficient ansatzes are needed for VQE to tackle more complicated problems. So for chemistry inspired, the main issue is basically circuit depth, where your circuits basically get too long. And for hardware efficient ansatzes, the main problem is usually barren plateaus and the simple number of parameters for classical optimization. And with that, I'd be happy to answer any questions.
So we have a couple of comments and questions in the chat. Maybe you can read Rob along.
Yeah, essentially if you want the exact solution for a quantum problem, and you say you want to just write down the state, not write down, save in memory the state of a system with like 50 qubits, you need 50 petabytes of RAM essentially, and this is not an efficient way to represent it. Obviously, you can get by throwing out some zeros, for example, you can improve it using sparse matrices and things like that. But the problem is still there. It scales exponentially, and the promise of quantum computing is that you can represent the 50 qubits, the molecule with 50 spin orbitals, you only need 50 qubits to represent it. Now there are its own problems, obviously, how to load this information on a quantum computer, how to read it out. There's many problems that I'm not going to get into, but when they do get bigger and we get better algorithm, there is this speed up is it's possible to get it. It doesn't mean that we are going to get it, but at least we know that this we have the QPE method that knows how to, that lets you solve the finite eigenvalues of the Hamiltonian with exponential speedup.
Yes, so that's correct. On the camera. Yes, the point is that there is a quantum chemistry problems you have by nature exponential in the size. These type of interactions are essential all interactions. For example, when you have a system, you add electron, you basically need to compute interactions with new electron with everybody else. And you can see easily how basically it goes up exponentially in size. And here you really take advantage of a Hilbert space, which is dramatically much larger compared to what classical computers can do. And that's, I would say, a key advantage here.
All right, so let's start with the first notebook, which is mapping the Fermatic problem to the qubit problem. This is a brief refresher on the electronic structure here. So there is the Hamiltonian, electronic Hamiltonian, the ground state energy that we are minimizing. And we start with the Hartree-Fock solution, which we, for VQE, we perform on the classical computer. And we also compute the one electron integrals HPQ and HPQRS. So that's an input to our VQE simulations. So the Qiskit is interfaced with the multiple quantum chemistry programs, Gaussian, Psi4, PyQuant, and PySCF. In this notebook, we're going to use the PySCF program. And we start with the example of the hydrogen 2 molecule. Here we import these packages, the PySCF driver that basically allows you to run PySCF from your script, and some other necessary modules. So first you set up the molecule with the parameters. Here you set geometry. So you have the first atom at 0.000 and the second one at the distance of 0.7 angstroms, which is equilibrium distance for hydrogen 2 molecule. You set the charge of the molecule, which is 0, and spin multiplicity, which is 2s plus 1, where s is the total spin. But these two electrons are paired here, so the multiplicity is 1, so a singlet state. And we set up this PySCF driver, where we pass the molecule units, which we're using as angstroms. And as a basis set, we use the minimal basis set that has one Gaussian basis function for each atomic orbital. Again, if you want to learn more, there is Qiskit has very nice manual, and there is also the textbook with some examples. So feel free, if you want to run something later, refer to their materials. So to refresh on the mapping, there are three main methods of mapping that are coded in Qiskit, and we will look at the Jordan-Wigner and parity mappings here. Again, we import more modules, so this second quantization module, where we import these modules for different mappings to set up electronic structure problem and to convert from fermions to qubits. So here, let me clear the... So we started with setting up the electronic structure problem, where we pass our driver that we set up over here, which is a PySCF driver. So we essentially want to run artifact and compute 1 and 2 electron integrals. And once we've done this, we can get our second quantized operators by calling this this function here. And if we print this, oh, sorry, I forgot to run the first cells. So you run all these imports, and here you have the second quantized operator, where here you have printed the coefficients that depend again on the molecular and nuclear distance, and these are A and A dagger creation annihilation operators. So here we read it from the last element, so this is going to be A0, A1 dagger, A2, A3 dagger. There's also these I operators that are simply identity operators, so we don't do anything to those qubits. And N is the number operator, which is A dagger acting on the same qubit. So this is our second quantized fermionic Hamiltonian. We want to map it onto qubits using Jordan-Wigner transform here. So we create this qubit converter object and pass this Jordan-Wigner mapper that we imported. And to get the qubit operator, we simply call the convert function on the qubit converter and pass this second quantized fermionic operator. And what we're getting is this qubit Hamiltonian, which has polystrings and the coefficients that depends on 1 and 2 electron integrals. Are there any questions up to this point? Is everything clear?
No, I don't see any questions.
All right. So this is the Jordan-Wigner mapping for H2 molecule using Jordan-Wigner transform. You can do a similar problem with Ravi-Kitaev mapping, which will also give you the same number of terms, but they might be different because it's a different mapping. And for larger problems, you will get a benefit that with Ravi-Kitaev, it will map on a smaller number of, you'll get smaller number of gates in your circuits. But to pick a smaller problem for this workshop, we're going to use the parity mapper, which allows to, because of the symmetry that it uses, it allows you to reduce the number of qubits in your problem by 2 by passing this 2-qubit reduction through. So when you do the conversion using the parity mapper, you only have these 5 terms here, one of which is identity. So this is going to be easier, and we won't have to wait long for calculations to run. And if you pass this with a default value of false, you're going to get the same number of terms as in other mappings, but we will stick with 2-qubit reduction so that we don't have to wait for long simulations. So this is the setup for the laser simulations to run VQE. So here we set up the electronic structure problem, we performed Hartree-Fock and computed 1 and 2 electron integrals. That all was done by PyCF electronic structure program. And then we used the different mappings to map the fermionic problem to the qubit problem. Are there any questions?
No questions.
All right, so if we are good here with this short notebook, I'll continue with the VQE. In the second notebook, need to import some modules there. This is in this cell, we're essentially repeating what was done in the previous notebook. And here we also compute, basically pull the data with number of particles and number of spin orbitals out of the electronic structure problem. And essentially we get number of alpha electrons, number of beta electrons, number of molecular orbitals. And again, we use parity mapping with the 2-qubit reduction. And we get this qubit Hamiltonian with 4 terms. So while it's thinking, since this problem is easily solvable on a classical computer, it's only has 4 orbitals and 2 electrons. We can get the exact solution for this problem using the essentially by diagonalizing this Hamiltonian directly to get the eigenvalues, and then compare. We have a reference value to compare our VQE results to. So we set up the minimum NumPy minimum eigensolver, and then call compute minimum eigenvalue on it with the H2 operator, which is this Hamiltonian here, and we get our reference value, and it's equal to this value. And again, this is the computed energy. To get the total energy, you need to add the if you want the total energy system, you would need to add the nuclear repulsion. But here we're only comparing the computed parts between the VQE and the exact solution, so we don't have to worry about this here. So we want to set up the unitary coupled cluster Danzatz with the with this UCC function, but before we set it up, we need to construct the initial state, which is going to be our Hartree-Fock state. So all the orbitals will be doubly occupied, and to construct it, you need to pass the number of spin orbitals to it, number of particles, and the mapping that you're using. So this initial state for any system with this number of spin orbitals and this number of particles using certain mapping is going to be the same for every system. So this only arranges electrons basically doubly occupied orbitals. And then after we construct the initial Hartree-Fock state, we can generate our unitary coupled cluster Danzatz, where we again pass the number of spin orbitals, number of electrons, our parity mapper, and here we can, with excitations parameter, we can set the truncation level. So remember when I was talking about the coupled cluster, you can generate single excitations from the reference Hartree-Fock configuration and double. You can get into triples and higher, but that gets very expensive, and it's not necessary for this molecule anyway, because it only has 2 electrons, so it's all covered by double excitations. But for larger molecules, some higher order excitations might be important. And we pass the initial state, Hartree-Fock state. So let's see what it gives us. So it prints the number of parameters that it generates, the depth of the circuit that is generated, and the actual circuit. So we have 3 parameters, so we have 3 excitations, and the depth of the circuit is 19, where depth is defined as not as number of gates, but the number of because some gates can be executed in parallel if they're acting on different qubits, and they count it as 1. They add the 1 to depth, so this particular Danzatz has depth of 19. Now we can look at the hardware efficient Danzatz, which is there's multiple ways to do this, but Qiskit has this to local to construct the hardware efficient Danzatz with gates that rotate around y-axis and controlled z gates as multi-qubit gates. And for this system, we get this circuit with 8 parameters, but with smaller depth. And as I've said, hardware efficient Danzatz is usually more compact, but has more variational parameters. So it has less multi-qubit gates, but more parameters. So, and as you can see, instead of 3 parameters in UCCSD, we get 8 parameters to optimize. Any questions up to this point?
Yes, there is a question about Why? Well, it's a discussion about Jordan Wigner versus Bravый Kitaev mapping. The question is, why did you use Jordan Wigner? Why not Bravый Kitaev, which scales better? Its basic question is about advantages and disadvantages of different mapping schemes.
Well, for Jordan Wigner gives you a better interpretation of what's sort of more chemical intuition because it maps directly orbitals to qubits. Bravý Kitaev is more complex, but it's correct that it's been shown that in terms of gates, you can get for larger systems, it's beneficial to use Bravý Kitaev method. But here with parity that I'm using here, you can actually get reduction in the number of qubits by 2, and granted, and given the problem that we only have 4 qubits, it's a reduction by a factor of 2. With Bravý Kitaev, we would have to deal with 4 qubits. And so here I picked it so we don't, so first of all, you can actually print the circuits and look at them because they're not as big and they're comprehensible, but just start with simple things. You can always make a problem harder very, very quickly and easily. Yeah. Anything else?
No, thank you. That's all.
All right, so let's start. Let's run the actual VQE simulation. So here in this cell, we're gonna run the VQE using the high-efficient Danzatz and BFGS optimization method, which I'll talk about optimizers a bit later. You can pick different ones. And you also have to provide this quantum instance, which is essentially tells you you have to tell Qiskit what to use as the backend. Either it's a state vector simulator that works with matrices and gives you exact solution, so it doesn't involve the process of probabilistic measurement as real quantum devices do. This can also be an error simulator, which will give you this probabilistic measurements, which I'm going to talk about in the next notebook. Or it can be any quantum device that you have access to. And so when we have this VQE object, we can simply call the compute minimum eigenvalue and pass our qubit Hamiltonian. And it does it very quickly. If you print the result, you can see that it's converged in 189 evaluations, gives you the eigenvector and the eigenvalue, which is our energy that we want, as well as variational parameters, the values of the all variational parameters. So this is the high-efficient Danzatz. We can do similar with the unitary coupled cluster. So instead of high-efficient, we pass this UCC Danzatz and the same simulator, same qubit Hamiltonian. And you can see we converge here with 20 iterations, and we optimized 3 parameters, and we got the energy that we're going to compare to exact value later. So up to here, you can see that the UCC Danzatz converge much faster, and sometimes when you run these simulations, when you don't see what's going on there, and you want to dig in and see how optimization is going, you can use this feature where you can monitor the convergence. And here we're going to use this to compare different classical optimizers, which are all optimizers can be good for certain problems and bad for other problems. For example, this optimizer SQP is not great for systems with noise, but it does very well for state vector simulator. Cobile optimizer doesn't have gradient, and BFGS uses gradient to optimize. But this is all to just show how optimizer can affect your results. So here we set this array of optimizers, and for each optimizer we're going to run the VQE and use this callback function to store intermediate results. We're going to store the number of evaluations and the average energy. And it also can give you the standard deviation of the energy, but in this case we don't need it because we're using state vector simulator that gives you always the same results because it works with by multiplying matrices. And so again, the same structure, we construct the VQE object with the Danzatz and optimizer that's gonna take the current optimizer from this list, and we use state vector simulator, and then we'll just store these arrays for plotting them later. And it's already complete, and we can plot the our results for hardware efficient Danzatz for different optimizers. And so, as you can see, they all converged within around 40 iterations. And now we can compare this to the unitary coupled cluster, which we do really the same thing, just replace this hardware efficient Danzatz with the coupled cluster. And we can run this optimization and do the plotting. So here, the most noticeable thing is everything is converged much faster, which is not a surprise. It has less parameters to optimize, and they get the similar performance. And here we remember when we computed the reference value, so exact solution. It's so that we can compare the error. We can calculate the error that we're getting from our VQE. And here is the energy error in Hartree, and this is the evaluation. So for hardware efficient Danzatz, we get this down to this the best error, as you can see, you get with the BFGS optimizer, and these two are they stopped earlier here. For the unitary couple cluster, this SLS QP optimizer works the best. It gives a small error rather quickly, and compiler here takes much longer. If you want to, so any questions?
No questions.
You also can use the gradient to speed up the calculation. So here, for computing the gradient using finite differences, you can pass this gradient object, and you can see that it's going to converge much faster. So here it only took the four iterations to converge to essentially the same energy. So this is how you do the simulations, VQE simulations on state vector simulator. And to reiterate again, this is the sort of simulation that's good for theoretical research, where you get the same result every time you run this, because it only works with matrices. There's no probabilistic component as in real quantum measurements. And this is not what happens when you do measurements on actual quantum computers, and that's going to be our next notebook. We can switch to notebook number 3. So here we're going to do the simulations with on air simulator that simulates the stochastic noise through the quantum measurements. And we'll also run simulations on a simulator of a real quantum device that has noise that you will get on a real quantum hardware. And also briefly, I'll show you how you can do measurement error mitigation in Qiskit. So after these imports, so here I just copied this qubit operator Hamiltonian from the previous notebooks. So this is the one with same number of terms, 2 qubits. Again, we do the exact solution. And we will start with running the simulations with stochastic noise, so no quantum noise for now. So to do it, we, as a backend, instead of state vector simulator, we use this air simulator, and we use this random seed so that all of us will get the same result, so that all the plots and everything looks the same on different devices. And here we use the optimizer that's better suited for the simulations with noise. It performs better, and we can run this using, here we use the hardware efficient Danzatz. And in the end, it is going to print us the error on a chasm simulator or air simulator and the difference from the reference value. And it's gonna take some time because with noise, it's harder for optimizer because you have uncertainties when you decide where to shift your parameters, and the more noise you have, the harder it can get. So it's still optimizing. And here's the answer. So here we get the energy, and the difference from reference energy is 0.01 Hartree. So it's 10 millihartree, which is more than the chemical accuracy. And we can plot this. As you can see, you have more oscillations here. This is a direct result of this stochastic noise I've been talking about. And even in the end, it's still oscillates, but around the right value. So now you can add noise to the simulations. We do it here using the mock devices. So here we use the fake Vigo device. This is a 5-qubit machine. And essentially everything is the same instead, except that we add the this block with that's responsible for the noise. So we basically set up where we're gonna run it, which is gonna be the simulator, and generate noise model from this fake device, and passing the basis gates that are implemented on that device. And we can run the simulation. So here we get the noise model object printed out, and it's running. Is everything clear up to this point? Any questions?
No questions.
All right. So once it's done, we're getting this plot for performance with noise, which looks similar. We just have more noise here, and it takes longer to converge. Let's wait for it to finish. And here, so as you can see, we have larger errors. We had 0.01 Hartree with just stochastic noise. With device noise, we're getting further from the real value, which is expected. And now, one of the easiest errors to mitigate is the measurement error mitigation, because it contributes a lot to the errors on the order of 10 to the minus 2. So 1-2% is a chance that when you read, when you're supposed to read 0, you're going to read 1, or vice versa. And so the way this measurement error mitigation works is you essentially run the empty circuits with just you just measure it and you use that information, how often it provides the wrong results, and you adjust use that information to adjust your results with your real circuits. So for that, it uses this Ignis package that comes with Qiskit, this complete mass measurement fitter is what it uses to do the error mitigation. And now, if you run this, it should give you a better value than we got in a previous cell where we only did it with noise and no error mitigation. Let's wait for it to finish. Any questions in the meantime?
No questions. Yeah, I suggest we wrap up rather soon.
Yeah, I just need to this is the end basically. So this is the plot for the measurements with the measurement error mitigation, and in the end, just look at sort of all the results that we got in this notebook, where without noise we get the best the 0.01 Hartree error from the reference exact value. When we run with noise, we get a much higher energy, but when we run with noise and measurement error mitigation, it gets much better, but still not as close as the noiseless simulation. And so Qiskit, so these are the really, really basic things that you can start with. Qiskit has a very nice documentation, and they also have the textbook that explains the main concepts and gives you examples. And they have the tutorials to when they release some new features, they always release it with tutorials, so you can try them yourself and play with it. And if there are any other questions, I'm happy to answer them.
Thank you very much, Dmitry. It was great. It's quite useful really to see how well it works under the hood. Thank you. Bye.